Thanks for coming out. Welcome to the Hilton Conquistador. Thanks for spending your evening with us. You're joining a whole group of LSST project members and community members interested in LSST this week. We're meeting the whole week here at the resort. We're really happy to be able to do this evening and have you participate. And look forward to engaging with you even after the talk if you're interested in sticking around. So my name is Victor Kravenbaum. I'm the project manager for LSST. I'm going to start us off with just a quick rundown on the status of LSST as it is today, the construction. It will be very hard to compress that into 15 minutes, and so you might find me going a little faster. Happy to talk to you afterwards and point out a few resources in a few minutes. But first, before I start off with those kinds of status ideas, I wanted to just remind us all of what is LSST. LSST stands for the Large Synoptic Survey Telescope. Our objective is to build an observing facility and then conduct a 10-year survey, as well as process all the images that we take, archive all those images, and then serve for both the raw images and the products that we can generate from those images. So that's our objective, and we'll reach that objective by building a new 8.5-meter class telescope, a huge camera that goes on that telescope, and a petascale data management system to be able to deal with the 20-odd terabytes of data that we produce every single night. That single survey that we will conduct for 10 years is designed to meet several different objectives. In the image on the right, you see a sort of accelerated animation of what the telescope will be doing every single night. It spends 30 seconds in any particular part of the sky and then moves on to the next one for 2 more images. And we take something like 5 million images in those 10 years, and we'll do that in any one of 6 filters, different optical bands and filters that we have available in the camera. And then those data products that I talked about come in different kinds, in a few different scales of time. So we take 2 15-second images, we can do some differencing and some adding, and so we have sort of, in 60 seconds, anything that's different between those will produce an alert. That's one of our data products. Also, every year or so, we will take all the data we've taken to date and reprocess it and make new catalogs and make generated data products. So those are the general idea for how we will conduct LSST after we finish construction. So to do this, we have a combination of federal funds and we have some very generous early private funding. We have $473 million coming from the National Science Foundation and $168 million coming from the Department of Energy. The Department of Energy is very focused on just building that camera that I mentioned, and I'll repeat in a few minutes. And then early on, before we were fully funded by the federal government, we had $40 precious million to start us off, to get the whole project started and really accelerate us into the project that we became with federal funds. LSST is a project that is vast. It is on a global scale. We have project members all over the globe, and those project members are both within the sort of managing organizations, but also in partner organizations. As you can see from the next few slides, dark blue is partners. The few managing organizations are in lighter colors. And by subsystem, you can sort of see the distribution of how we've developed the program using all of those resources that we could get on the global scale. So here's data management. The camera was developed by roughly half from the Department of Energy labs in the light blue, and then about just as many private contractors. And then the telescope and site was built heavily from private contractors, just taking advantage of the industry capabilities across the globe. And then EPO is also being executed, also looking for who's got the expertise and the kinds of things we want to do to bring LSST, not just to our science community, but also to the public. So here's an image taken just the other day. I mentioned to you that we are here in force this week. There's 300 or so people that have come together. We've been doing this for about 9 years as a collaboration meeting to bring the entire team together for both the construction, but again, now also very focused on getting ready for this onslaught of data and making sure that our scientists are ready to take advantage of LSST when it does come online. So again, I mentioned that we're going really fast tonight. I will point out to you that online we have many of these. In fact, tonight will be recorded and available to you, but also in previous years. The talks that we've given are also available on YouTube and available for pleasure listening and watching. So in about the 2012 timeframe, we were predominantly just ideas and designs, as you can see from the lower right image. That's an image of our summit facility as we predicted it would look and as we were designing it. On the top left is a current image as of June. And so when we started construction in 2014 with those federal funds, 5 years or so have gotten us to the point you can see there on the summit. And as of today, it looks pretty similar to what I did in June, but here's just to point out that you can also follow our progress on this public webpage that's available every day to see the progress as it progresses each year. So if you saw the images in some of the videos at the beginning of the evening here, you saw a lot of mirrors, a lot of mirror video. This is a picture of our primary mirror. It's particularly unique because it has both the primary reflective surface, that's the first reflection, as well as the third reflection. That's why you see two very distinct shapes. And this is the first time at this scale anybody has ever put two optical surfaces into one piece of glass of this size. This was done right here at the University of Arizona. And what we then had to do was take that 17 tons of glass and turn it into an actual mirror. It takes more than just glass. And so over the last several years, we've been spending a lot of time building the 30 tons or so of steel structure and mechanics that is required to hold up that mirror to the kind of tolerances that are required to make it successful as an optical collecting aperture. Also, what you saw, there's a still image you saw in the images. We had the opportunity just in January of this year to put all of those pieces back together again with the glass, seeing the structure that supports it for the first time. We had the opportunity to do that here in the laboratory, which we don't often get, so that we could do some really high fidelity testing of the glass, making sure that we can control it properly with this new hardware. And after that very successful testing in January, we started the long road from Tucson to Chile. And you can see here that it's not just a slow road, slow drive to Houston, but it's also particularly longer because you don't get to go in a straight line when you're driving for something that big. You do eventually get to the port, but you also don't get to pick the weather. And between here and Texas, you can confront almost anything. You do eventually get to a port in Houston, and things go a lot smoother once you get on a ship, but if you're familiar with what it takes to go from the port in Chile to our mountaintop, we also do have to go through one particular tunnel. So I'm happy to report that it did fit, and it worked out smoothly, and the mirror made it fine to the summit. Also going through that tunnel was the massive vacuum facility that it takes to make a cooling facility. And so that chamber there on the left was also assembled. That is a picture of the coating plant in our facility on the summit and was recently completed, as I said, but also had to do that same journey, except even further because it came from Germany, but also successfully made it through the tunnel and was successfully executed our first coating. We happened to have our secondary mirror already on the summit, and so once that coating facility was purchased or bought off from our vendor, we immediately turned around, got our team prepped, and put our secondary mirror here that you can see in the bottom into that chamber to put a silver coating. It's actually protected silver coating. On the top left are a couple images. Also, you would have seen in the video, it's like rotating magnetrons. That was the coating facility, the coating chamber doing the actual coating of that mirror. So if you envision the optics that we have, in the background is the M1, M3 mirror, and the foreground is the secondary mirror with its back to us, and then the cameras in the middle. Now we have to take those optics and cameras and hold them, and so that's what we call a telescope. And so this is a rendering of that telescope. It's particularly difficult because of the cadence that we have to run with our survey. It requires an extremely stiff structure because we have to hold those elements in place, but also be ready to move from position to position to position all night long very rapidly and not waste any time in dampening out the system. Happy to say that that whole telescope was assembled in Spain. There's an image of it in its testing, or video of it during its testing, and was completed. Here's an image of it in the test facility in Spain with the large number of dedicated staff that it took to fabricate all of that part, all those parts, and assemble it. Before we disassembled, have it put it on a ship, and as we speak, is traversing, I believe, on the Atlantic, scheduled to be in Chile in the first week of September. As I said, we have a very unique and a very large camera that's necessary to collect all the light that we can gather from those optics. This particular camera has a front lens of 1.6 meters. That's 5.5 feet, 5.5 feet, so if it were laying here, it would be up to about here. It's about 3 tons, carries 5 of those 6 filters that I mentioned that we've been taking the images in. So the 6th one sits on the outside and we can put it in during the day. At the heart of that camera is, of course, the focal plane. That's what collects actually the light. And what we do with that is we've built up that focal plane to get to the 3.2 billion pixels. We do that with 189 individual 1 inch by 1 inch, 4,000 pixel by 4,000 pixel sensors. And so circled there, in the middle of the screen, is one of those sensors. We take one sensor, pack it in with 8 others to make a raft, and we have 21 of those rafts to make the entire focal plane. That focal plane is about a manhole cover, 63 centimeters in diameter. In the lower right is one of those rafts. They're so closely packed together, that's actually 9 sensors in that bottom image to the right. You can barely tell the difference between one sensor and the next. Happy to report that all the sensors we need, plus many extras, the engineering grade sensors, but most importantly, those 189 science sensors are delivered by our 2 vendors, one of which was right here at the University of Arizona as well. We've taken all of those delivered sensors and made all the rafts. And so progress is progressing very well with the camera. And here is an image in the integration hall of the camera facility. In the top left is the empty camera, looking just into the face of it without the optics. And then the images on the lower right, successively down, is the start of the integration, the installation of those rafts that will start to become that fully populated focal plane. The optics I mentioned were 1.6 meters in diameter. Those are massive. Those are some of the largest lenses we would build for a camera. And happy to report that those were also completed. In fact, they were completed right here in Arizona as well, and were delivered today to the facility in California, where they were made up with the sensors, and the whole camera will start to be assembled at the facility at the Stanford University. Okay, so that's sort of a quick list of the observing structure, the observing system, and then of course there's that data system that we need. And I just wanted to quickly point out that we have prepared all of the network agreements necessary to move all of that data from our mountaintop in Chile and South America to our large data facility in the continental US through the networks required to move about 100 gigabits per second on a protected network. So that we can get all of that image data to the facility as rapidly as possible, so we can just keep up with all the data that we're taking. And as well as the networks, of course, it takes an enormous amount of computing power that is also in the process of being assembled with the large amount of software that is also necessary to take each raw image and, for example, take that raw image and make it a calibrated image, and then turn that calibrated image into something that we can serve to the public or start to process and make those data products. Last year, at this time in the talk, we focused a lot on our education and public outreach program. We wanted to make sure that this large, brand new facility producing this very unique data set was immediately able to not just serve our professional scientists, but also was ready to serve the general public. And so we made sure that we embedded into the construction project part and a group that would focus specifically on how to bring the data and the science to our public audience. And that includes working with formal education groups. And so in the top left, you see one example of a formal education type program that's already been demoed and tested with some various groups, as well as other audiences like the top right, which is the planetariums. Is another place for us to outreach to the community. And so we're also already working on assets that can go into those formats and be available for planetariums, as well as making sure that we aren't just serving our English-speaking communities, but particularly because we're in Chile, we wanted to make sure that we emphasize our Spanish-speaking community as well. So we're working a lot on making sure that it translates well, not just in language, but in principle and in concept and culturally. So all of this continues to be on track, on schedule. I mentioned we started in 2014, and we are on track to have our first flight in 2021, and we'll be on sky observing, starting our 10-year survey starting in 2022. So that is LSST construction. When we're done, I'm happy to take questions, but in the meantime, I will pass the baton, and we'll go from construction to science.
Good evening. Thank you for that lovely introduction to LSST. Tonight's lecture is about LSST and black holes. As we are gearing up towards the exciting results from LSST, we are also doing other things to increase our understanding of black holes. For example, this past year, the Magellan Telescope released the first image of a black hole. And I was heavily involved in that project. So I want to tell you a little bit about how that project came about, and you will see a lot of parallels with what you just heard about LSST. Constructing telescopes that are specific to our goals, the large data volume, the international and large collaborations that are needed to get us there. But before that, let me start with, what is a black hole? We talk a lot about them. We know or claim that they exist in our universe, within our galaxy and in other galaxies. So black holes are a very natural prediction of Einstein's theory of general relativity. How gravity works was revolutionized by Einstein. He wrote down his famous equations, and even though he himself never believed it, he hated the idea that his own theory predicted the existence of these infinities, these extreme objects in the universe that are basically cut off from the rest of the communicable universe. So he hated that. But other people developed the idea that there are going to be these, when you bend space and time, there are going to be these regions that actually are so massive and so compact that they're going to absorb all the light around them, all the mass around them, and they're going to be just these black objects that an observer can't see. So to illustrate that, I have a little animation here. According to Einstein's theory of gravity, both light and matter travel in straight paths, just like this, in the absence of an object that bends the space-time. But let's now put an object. What I made here is a black hole. So light and matter are still going to follow their paths on this now stretched fabric. They don't know any better. It's like ants walking on a watermelon. They don't think they're walking on something curved. Just because the sheet is curved, light and matter doesn't know any better. But what happens is that this curvature is so extreme that some of the light gets trapped in it. As you can see in the simulation, some of the light that comes too close to the black hole never makes it back out. So let's go from the animation to actual computer simulations that we use to understand black hole environments and to guide our observations. So what I will show you here is some of the earliest large-scale simulations we've done here at the University of Arizona using a technology called GPUs, graphics processors units. They're actually available everywhere. They're on your computer, they're on your phone, But what we did was start using them to solve equations. So instead of just having it be a graphics display on your phone, we started doing this. So here my colleague C.K. Chan at the University of Arizona is demonstrating how fast we can render these, how we can run and render these simulations. He's initializing the simulation using his hands, and this device is called Leap Motion, just so he can control many thousand lines of code just by waving his hands. And he can run the simulation forward and backward with a black hole at the center, millions of light particles going towards it. And what you see is that a lot of them get deflected and leave a hole at the center. So our prediction is that if we could take a picture of a black hole, there would be a black hole at the center of that picture. It would swallow some of the surrounding light that comes from all this gas swirling around it and leave this hole. Okay, so we have to start by picking a target. We said, okay, of all the black holes that we suspect are present around us, where should we look if we're going to take this picture and see if this hole that we predict, according to these simulations, is it really there? So we picked not the black hole at the center of our own galaxy as our first target, but we picked a relatively nearby galaxy called M87. So how you can find it in the sky is you go to the Virgo cluster, here are the arms of the Virgin, so it's somewhere here. Let's zoom in, these are all real images. And M87 is in this Virgo cluster of galaxies, not the most massive one, but the brightest one of that cluster. It's sitting right here. So tonight, if you'd like, you can go out and look at where M87 is. Let's keep zooming in. So what do we know about M87? We know that when we look at the very center, the heart of that galaxy, something interesting happens. We've known about this for about 100 years. There is what we call a jet, an outflow of energy and matter that is traced back to the very heart of that galaxy. The only objects we know of in the universe that are capable of launching such powerful jets are black holes. So we've suspected for a long time that there must be something very powerful, very massive, and acting like a black hole there. So I said we carefully picked our targets because, you know, we want to take a picture. And the bigger the picture, the more detail we can see. Well, how big is it? I'll give you an idea. What is this? The moon. How big is the moon? Half a degree, right? If I, at arm's length, one finger width is a degree in the sky. Okay. So we start with that. We divide it into 60 arc minutes. Just like we divide an hour into minutes, we divide a degree into 60 arc minutes. We take that, and each one of them we divide into 60 arc seconds. We take that, and each arc second is 1,000 milliarc seconds. And we take that, and that is 1,000 microarc seconds. If our theory is correct, the image that we're going after to photograph, the black hole that we're going after to photograph, is about 40 microarc seconds across. Okay? So just think about how tiny, tiny an angular size that is in the sky. Now, we have, so the equivalent of putting a donut on the moon and then saying, take a picture of that from the Earth. Okay? That's what we're after. Slightly crazy, but you know, some projects need to be crazy. So, the resolving power of a telescope goes with its diameter. Here is a fancy Vanguard telescope. Here is the beautiful LSST that we've just seen the construction of. That is going to be revolutionizing. And here is another project that the University of Arizona is leading. It's being polished in the NOIRLab, the giant Magellan Telescope. Now, these are not only enough to resolve that scale that we want to see, they're also not the right wavelength. We want to go to slightly longer wavelengths towards radio, to a millimeter wave. And we want to build something that is simply the size of the Earth, okay? Not any bigger. So, just like LSST, we went to the NSF and we said, could you give us money to build an Earth-sized telescope? And they said no. But the good news is that we are actually kind of smart and we can sometimes outsmart nature. If we can't build a dish that is as big as the Earth in order to resolve that tiny scale, we can pretend that our telescope is that big by putting telescopes all across the globe, for example, one here and one here, looking at our black hole at the same time and recording the data faithfully, so that after the fact, we can take them, put them on a correlator, match up the light that they have seen, and the collecting power won't be like the entire Earth, but the resolving power will be like the entire Earth. This is a technique called interferometry, has been developed over decades. So we said, okay, let's go ahead and do this. So over the past decade, we've built what is known as the Event Horizon Telescope Network. Here is a virtual tour that starts off in Spain, the Iron 30-meter telescope on the Pyrenees. In South America, in Atacama Desert, the ALMA telescope and the Apex telescope. Closer home in Mexico, LMT, and right here, our sub-millimeter telescope in Arizona, to Hawaii, two telescopes, JCMT and SMA, and our farthest one, just because we want the largest aperture possible, the one in the South Pole telescope. For about a decade, we outfitted all of these telescopes. We put masers on them, we put data recording devices on them, and we put receivers on them. So this, as of 2017, when we did the first worldwide observations, this was the setup of the Event Horizon Telescope array. And in the meantime, the collaboration has also grown. This is from a meeting in late 2018 in Nijmegen. And this is our University of Arizona team. Undergraduates, graduates, postdocs, several faculty members. We are fully vested in making this happen. And just because we're a proud group, again, here this is Mount Graham that we operate and outfit, and this is the South Pole Telescope that we outfitted and operated for the purposes of the EHT, the Event Horizon Telescope, even though it's a University of Chicago telescope. In April of 2017, all of these telescopes simultaneously turned their gaze to the black holes that we picked in the sky, the one at the center of M87, as well as the one at the center of our galaxy. But I'm not going to talk about give you the results of that tonight. Happy faces, it means it was good weather everywhere. We obtained 5 beautiful nights of observations, lots and lots of data. Of how much data? A lot of data. And this is the control center in Cambridge, Massachusetts. I'm right here. And we started trying to combine and analyze these data. So these are the locations of the telescopes that I already showed you. These are the 2 correlator centers where the signals are going to be combined into one. This is in Bonn, Germany, and this is MIT Haystack Observatory. So we took 5 petabytes of data over the course of 5 nights. It is even a higher data rate than LSST. But what saves us is that we observe for a little while, and then we stop and then spend a year analyzing it. Okay? As opposed to LSST, where the data is going to just keep on coming night after night. And then we sent the data, the correlated data, to all of these places where we analyzed it, fit our models to it. So 5 terabytes were transferred to the Google Cloud across, and finally we released our results. So the timeline was April of 2017, the EHT array. The amount of data weighed more than half a ton in disks. It is so much that transferring it over the the available speed on the internet, not just from the South Pole, but anywhere, would have taken years. So we physically shipped them. We put them in crates, and then we put them on FedEx trucks, and we had to wait for the South Pole summer to come, and physically ship these crates out, and for the most part, they made it okay. Then we correlated them, which reduced the data by a factor of 1,000. Then we went through a process called fringe fitting, basically fitting the exact form of light that gave rise to that. That reduced it by another factor of 10,000. Then we put our imaging algorithms to use, and then finally, this is the picture you may have seen, and we had our announcement in April of 2019. This is it. It was even more amazing than we expected, even though I said there should be some light around it that escapes, and there should be a black hole at the center. When you actually see it, it's something else. And we were very happy that everybody else thought that after all of the sleepless nights and a decade of work. So these are all the major newspapers the next day. But honestly, my absolute favorite was not the newspaper coverage. It was the memes that people came up with. Here it is. And I fully take responsibility for this because we said the size of a donut on the moon so many times that once we had the image, yes, why can't you do it? But it was like a half-eaten donut. So, I already showed you in the beginning some simulations that we did based on Einstein's theory of general relativity, just to understand what black hole environments are like, and I showed you that animation of just shooting light rays, but that's not where it stops really. We still have to understand how black holes get gas from their environments. Right? There are going to be stars, there's going to be gas around it, it's going to swirl in. We're going to make very detailed predictions of how gas gets there, how it emits light, and what part of it gets swollen by the black hole, if we are going to understand it. So we built these more sophisticated models, and here is an image gallery from the hundreds of simulations that we have run, just to make sure that what we're predicting, what we think we are understanding, is in line with, or it matches or doesn't match what we observe. So we followed all the possibilities that we could, and this is just that gallery. And because we ran so many different types of what-if scenarios, we were able to use all of those theoretical simulations in order to take this image and ask, okay, what is the mass of the black hole that gave rise to this image? And it turns out to be quite simple, because when you look at the bright parts of it and you put a ring to it, it's a little bit more complicated than that, but I'm going to gloss over it. The size of 42 microarcseconds, that unit I introduced in the beginning, corresponds to a black hole mass of 6.5 billion times the mass of our sun. 6.5 billion times the mass of our sun. That's how massive that black hole is. Okay? And what is amazing is that we have an independent estimate of that black hole's mass just by watching the stars around it move in orbits. Just basically Kepler's laws. Okay? So, amazingly, that prediction is very close to 6.5 billion. So whether you trace stars around it or go and take an image and use your most sophisticated model to measure the mass of the black hole, it's 6.5 billion solar masses. This is just one aspect out of many that we want to understand about black holes. There are so many questions surrounding them. Anything from the very first black hole in the universe. When did it form? How big was it? How did it grow? How did they affect the galaxies that they resided in? To come closer home. How many black holes are there in our own galaxy, the small kinds? And anything in between. that LIGO is making headways on, LSST is poised to make major discoveries on. And on that note, I would just like to turn it over to Rafaela, who's going to tell us about black holes of all sizes and what is in store for us.
All right, thank you, Ariel. Thank you for being here, and thank you for having me. So, in the next 15 minutes, I would like to take you on a tour of the different black hole masses that are out there. So, Ariel told us something about the biggest black holes that are in our universe, those that are millions or billions times the mass of the sun. But black holes come in a huge variety of masses, all the way down to the tiny little amount of mass of the sun. And we do also have expectation that an intermediate class of black holes should exist in between the 1 solar mass and the million times solar masses. So these black holes have very different sizes, but they share one key ingredient, which is their extreme gravity. And Ariel already told us how that works. Not only that, but black holes are black. But there is one way that we have to make black holes shine. And that one way is to feed the black hole with something. And different black holes feed on different stuff. So the most massive ones, like the one that Ariel just described, feed on the gas of their own galaxies. Some other times, these big black holes happen to eat one of those stars that wander around them. If we go down to the smallest black holes, where, those black holes sometimes they live in a couple, they live together with a normal star. And their gravity is so strong that they just steal mass from their companion. They eat that and they shine that way. And then there is another class of black holes, the cannibals. So those are black holes that eat their own star, the star that produced them. And tonight, I'd like to take you on this little tour and try to understand how we can use LSST to learn and reveal all of these types of black holes in our universe. So let's get started with the small ones. So when we look up in the night skies, and here in Arizona we have some beautiful skies, we might be misled and to believe that what we're looking at is peaceful beauty. Instead, what we're looking at is light that comes from a fight for survival. So those stars are shining in their attempts to fight against their own gravity. Gravity will like them to collapse. So the stars, to survive, they initiate fusion, they produce photons. And those photons that are those that make them shine bright are those that prevent them from collapsing. However, at some point, fuel is over, and fuel for a star is hydrogen. So what happens is that gravity wins. Gravity always wins at the end. The star starts to collapse, and that initial collapse is later counterbalanced and becomes an explosion. Stellar explosions, also known as supernovae, are a very common outcome for stars that are at least 10 times our own sun. So if now going to a real picture, this is a real picture of what is left behind from a stellar explosion that happened 1,000 years ago. It's the Nebula, a beautiful nebula in our sky. And if we zoom in, those are real images, those are not animations. If you zoom in, we can actually see what has been produced deep down there. This is a neutron star. And I will tell you in a second what a neutron star is. So bottom line, the key thing that I'd like you to take away from this slide is that if you wait 1,000 years, we can see what is produced by the explosion, what is produced deep down by the star collapsing. However, we do not see what is produced by a stellar explosion right away. And the reason is pretty simple, and here is how it works. Suppose that we have our big star. That big star runs out of fuel, collapses, produces a black hole in its core. That black hole is here, but in no way we can see what that black hole is producing. that black hole is accreting and eating the mass of its own star, but we can't see it. Why? Because there is all of this mass from the star that prevents any light from coming up. However, with time, the explosion expands, and this matter dilutes around. So at some point, what happens is that there is low density enough for these photons to come out. And at that point, we can see our neutron star, our black hole that was formed. So this is a typical normal stellar explosion. By now, I think you already understand that if, by any chance, the universe also produces explosions, stellar explosions that are born not with a thick blanket, so not with a large amount of matter around, but just a little tiny amount of matter around, well, in that case, it's way easier for the photons produced by the black hole sitting deep down to shine, and so we can see the black hole right away. So, bottom line, if those things exist, we should be able to see how black holes look like right at the time of formation. And until June 2018, if you were to ask me, have we ever seen something like that, I'd have told you no. But things changed on June 2018. So this is really the frontier of discovery. This is where LSST is going to play a huge game. So here is what happened in June 2018. A new transient was found in the sky. So what we do is very simple. We keep taking images, just like LSST would do, and then we do differences. And we ask ourselves, is there something new with respect to the previous time? Yes or no? So we found this new transient, and we are not very creative. We call it AT, Astronomical Transient. 2018 is the year. And then we start naming stuff with AAA, the first transient in 2018, AAB for the second one, and so on. And this poor thing just happened to be COW. So this is how the following day, every astronomer would be speaking like, oh, what is the cow doing? But that's what they mean. I mean, what is this transient doing? All right, so this cow transient is exactly one of these explosions that only had a very tiny amount of mass around. So let me explain you what that means. So what you have here is luminosity versus time. And a normal stellar explosion usually takes 20 days to reach the peak of luminosity. And it's crazy luminous. It's 10 billion times the sun. So star, when it dies, it becomes as luminous as its entire galaxy. It's quite amazing. But here is what a cow did. So it did go to peak in 2 days. And it was much more luminous, like 1,000 billion times the sun. And by studying the cow across the entire electromagnetic spectrum with a whole fleet of NASA spacecraft, radio antennae, and telescopes, including the MNT here in Arizona, we were able to understand that what was causing this weird behavior, this crazy luminosity, was the birth of a black hole by the collapse of the star. This is the first time we could witness this phenomenon in real time. And where does LSST come into this picture? Well, these explosions are rare. So if we want to learn what black holes do right at the time of their formation, we have to find more. And if you want to find more, you need big eyes. This is what LSST is going to do for us. Okay, so by now I told you method one. If you want to produce a black hole, the first thing you can do is to make a big star explosion. But I'm going to give you a few other methods, a few recipes to produce a black hole. So another option that you have is take two neutron stars, make them collide. So what is a neutron star? Well, a neutron star is the most compact star we know of. It has the mass, roughly the mass of our sun, in 10 kilometers. Super compact. And neutron stars are also produced by stellar explosions, and I can even point at it. This is a neutron star produced by this explosion 1,000 years ago. So we do know how to produce one neutron star, which is explode a star. So how do we go about having two? Well, we start with two stars. And in nature, what happens is that the biggest stars are the ones that run out of fuel the earlier. And so the first big star in the system will explode. And the companion has to survive bound to the system. which only happens in a very low percentage of cases. At some point, the other star will also go boom. And also the system has to survive. And if this happens, if the system is able to go through this two very violent steps in their lifetime, well, then you have two neutron stars. Okay, so now you know how to produce one neutron star, we know how to produce two. So why they can't just stay there and rotate around each other? Why they have to collide? The answer is simple, and it has to do with gravity again. These objects are so compact that the amount of energy that they lose through gravitational waves, which is also a prediction from Einstein's theory of relativity, is important. And so what happens is the following. These two neutron stars lose energy and they start rotating faster and faster and faster, and at some point they merge. And when they merge, they also produce a very luminous transient, a very luminous signal in our sky that lasts for 1 or 2 weeks. So let me play this again. So we start with two neutron stars, they can't stay there, they lose energy, and at some point they merge. When that happens, it's an extremely violent event in our universe, and they produce light. So this is something that we have actually detected. And this happens on August 17, 2017, almost 2 years ago. So for the first time on that day, we were able to detect gravitational waves and light from the same celestial object. This was an effort by more than 3,000 scientists around the globe, so it's a massive effort. So huge teams are involved. And not only we could find light, the type of light that we can see with our own eye, but we are also able to find radio waves and X-rays. This is the first time we could witness in real time two neutron stars colliding, producing what? A black hole. Here we go. So where does LSST come into the game here? So the gravitational wave experiments that we have right now are fantastic, amazing, but their localization capabilities are not as good as in the optical. So what happens, what means is that when we receive an alert from the gravitational wave experiment, they tell us there is something that happens around there. Go and figure out where that really happens. And inside that error circle, there are many potential galaxies, many potential locations where that neutron star merger might have happened. So what we do, and what we need to do, is something as simple as that. We have to tile. We have to tile the field and understand, is there something new that wasn't there the previous night that is most likely related to the neutron star merger? So that's what we have to do. LSST has a unique combination of sensitivity, has a big eye, can see very deep, but also has wide eyes, so it can cover a large area. So we can actually tile that field very fast. That's why LSST is going to play a huge role in this game of chasing after neutron star mergers in our universe. All right, so third way, let's get two black holes colliding. And two black holes will produce also a black hole. That's the other way to produce a black hole in nature. And I'm sure you've heard a couple of years ago, well, around 3 years ago, the announcement of the first detection of gravitational waves from two black holes colliding. Here is in animation. This is not how things look like in reality. The black dots are the black holes, and you can see them because they produce distortion in the light of objects around. And again, they can't stay there. Why? Because they're losing energy through the gravitational waves, wave emission, and what they produce is the black hole. Okay, so while for two neutron stars, we have seen some light, in the case of two black hole collisions, we have never seen any light coming out. So LSST will enable the deepest search. It's literally the frontier of research right now. Okay, so we made two black holes collide, we made two neutron stars collide. Guess what? Let's take a black hole and a neutron star, and they also produce a black hole. Just like the black hole mergers that have never been observed. And actually, this is something I'd like to share with you. I am here with no sleep at all. Why? Because last night we had one of these events. And if any of you is interested to get updates about what's going on in the universe, there is a beautiful LIGO app, and you can receive alerts at any possible time of day and night about when a new black hole merger happened, a neutron star merger happened, and you can see in real time what we are doing. But bottom line, this is what I did last night. We received this map. This is a map of the sky that tells us that here, somewhere here, something interesting happened. This is a neutron star black hole merger. And after a while, the gravitational wave people were able to refine the localization, and they were able to tell us, yeah, look here is better. And right now my team is going through all the images and trying to understand if something new was born. So stay tuned. All right, let's circle back to the big black holes. So Ferial was telling us about the very big supermassive black hole that sits deep down in M87, and this is the black hole that is kind of nice to us because it makes its presence very obvious because it's producing this jet. However, not every big black hole is that nice. And there is a huge population of supermassive black holes that sit there quietly in their galaxies. They don't do anything. We call them dormant black holes. And if nothing happens, we have no way to tell that a black hole is there. But in the recent years, we developed this technique. So we built on bad luck. On the bad luck of a star that just happens to wander too closely to the black hole. So here you don't see anything due to the black hole, and here is the poor star that gets too close. It gets ripped apart, and half of its mass go and feed the black hole. So the black hole that was dormant until that point wakes up and produces a jet. One jet just like the M87 one. And after a while, the matter from the star is over and the jet shuts off. So this is an artistic impression. Things look this nice only when they are not real. But look at this is reality, how things look like. So what we saw is this flare of X-rays. So nothing was there before, a huge flare of X-rays and gone forever. And here is the point where, okay, here the star gets accreted, we produce a lot of energy, and at this point the jet shuts off. Equal, the black hole has eaten up all the mass. That's it. So you have to wait for another star to go through. So where does LSST come to the game here? Well, this type of event are rare, thankfully for stars. They are rare, which means that if I want to learn about these dormant black holes, I have to monitor a huge number of galaxies. And this is again where the big eyes of LSST are going to make the difference. They're going to tell us, hey, look there, because right there something is new. So this black hole just is now alive. Okay, so this is the end of my little tour into the life of black holes, but as somebody said, the end is just where we start. And at this point, I think I'm happy to take questions, and I would invite the other two speakers to the podium as well. Thank you so much.